In this video, we'll talk about sequences, more precisely limit of sequences. So we have this example where a sequence is written as a sub n in between curly brackets when n equals 0 to infinity. And a sub n is given by 1 over n squared plus 1, and again n equals 0 to infinity, where n is 0, 1, 2, 3, and so on. Whole numbers. So if you set n equal to 0 and you replace it in this expression, we get 1. If n equals 1 in this expression, we end up with the next element of the sequence or term, a half. If n equals 2 replaced in here, we get 1/5, and so on. So what do we notice? We notice that the terms remain positive. We have only positive numbers, and they decrease to 0. So we say that this sequence converges and its limit is 0, and the notation is limit as n is approaching infinity of a sub n equals 0. Other sequences and other sequences that actually converge. So the sequence is given here, a sub n equals n to 3 over 2 over n to 3 over 2 plus 1. And these points here were obtained by giving to n the value of 1, 2, 3, 4, 5, and so on. So just by looking at the points, the terms that of the sequence that we get here, the limit as n is approaching infinity of a sub n is equal to 1. Another type of sequence is, the sequence is a sub n equals 0.75 to the n. So if you give n value of 1, you get 0.75. For 2, we get this value. For 3, this one, and so on. So for larger and larger values of n, like imagine calculate 0.75 to 100. What happens? Well, we are getting values closer and closer to 0. So one thing that you want to record somewhere, because r is between 0 and 1, which means we got 0.75. That's our r that they are talking about. Because this number is between 0 and 1, the sequence converges monotonically to 0. So basically, if we had another value like 0.3 to the n, the same thing will happen. It will converge to 0. 0.2 to the n, and so on, it will converge to 0 if we choose any value between 0 and 1. Now let's see what happens if we get a sequence like the one that we had before, 0.75 to the n, but this time is negative 0.75 to the n. Well, when n is 0, we get 1. So here, when n equals 1, we get negative 0.75, which is this point. When n equals 2, we get 0.75 to the second, which is 0.5625. So it would be this point here, positive. But we notice that when n equals 3, we're going to get negative 0.75 to the third, which is negative some number. So what we notice is that our terms alternate. For 0 it's positive, for 2 it's positive, while for 1 and the other odd numbers we get negative values. But even though it alternates, it actually ends up being converged to 0. So let's take a look at a few sequences that are more popular, algebraic sequences, and then we'll see the geometric sequences. Now, algebraic sequences, let me give you a very simple example. 2, 5, 8, 11, 14. Let's see, did you get the idea? How do I get to the next term? I add the same value. So if I add 3 to the previous number, I'm actually going to get the next number. So when we have this common ratio r equals 3 in our case, which is the difference between any consecutive terms, then we have an algebraic sequence. So basically, a sub 2 is a sub 1 plus 3. A sub 3 is a sub 2 plus 3. A sub 4 it's a sub 3 plus 3. Or in other words, a sub n it's the previous one plus r. Or in terms of the first one, it's a sub n equals a sub 1 plus n minus 1 r. How did they get that? Well, just think about it. This one can be written a sub 1 plus 3, which is a sub 1 plus 2 times 3. This is a sub 1 plus 2 times 3 plus a 3, so it's a sub 1 plus 3 times 3. So in other words, a sub n, it's the first term plus, you see how here it's plus 1, 3, 2, 3, so the connection is between this term and this one, between this one and this one, it's 1 less. So it's n minus 1 times 3 or times r in general. S sub n, so if I want to find the sum of the n terms of an algebraic sequence, we write the first term plus the last term times the number of terms over 2. So a popular sum like that, it's the sum 1 plus 2 plus 3 plus dot 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 plus n, which shows up in many problems. It's the first term plus the last term times the number of terms over 2. It is an algebraic sequence because the terms 1, 2, 3, 4, and so on have a common ratio of 1. Now, geometric sequences. Well, a very common example of a geometric sequence is 1, 2, 4, 8, 16, and so on. It's basically 2 to 0, 2 to 1, 2 to 2, 2 to 3, 2 to 4, and so on. So to get from one term to the next one, we are actually multiplying by 2, which is called the common quotient. So we can say a sub 1 is 1, a sub 2 is 2 to the first, a sub 3 is 2 to the second. So in other words, in our case, a sub n is going to be 2 to n minus 1. In general, a sub n is the previous term times the quotient, or the n term is the first term times r to n minus 1. Here, just correction, n goes from 1, 2, 3, and so on. I chose to start with 0. The sum of the first n terms is a sub 1 times r to the n minus 1 over r minus 1. So in our specific problem, if I want to find S sub n, is going to be the first term, which is 1, times r, which is the quotient, common quotient, which is 2, to the number of terms. So if I go all the way to 2 to the n, for example, then the number of terms from 1 to 2 to the n would be n plus 1 minus 1 over 2 minus 1, or in another case 2 to n plus 1 minus 1. Now, why am I saying that here we have n plus 1 terms? Because this is going to 2 to the n, right? So the 0 term 1, 2, 3, 4 until n. From 1 to n, there are n terms. From 1 to n, n terms. And then there is this term with 0, so it's that's why we have n plus 1. So let's take a look at this problem. Check if the sequence converges, diverges, or oscillate. So we have 2 to 0, 2 to 1, 2 to 2, 2 to third, and so on. So we actually can plot the point. So for 0, we get 1. 1. For 1, we get 2. For 2, we get 4. For 3, we have 8. For 4, we have 16 all the way. So basically, if we take a look what's happening with the terms? The terms are increasing. They are all positive and they are increasing, going to infinity, right? So this sequence is not convergent. Not convergent. Or doesn't converge. Let's take a look at 1 over 2 to the n. So if we give values n and 1 over 2 to the n, if n is 0, we get 1. If n is 1, it's 0.5. If n is 2, is 0.25. If n is 3, is 0.125. So if we plot this in a coordinate plane, n and 1 over 2 to the n, we get this, which obviously the terms, what happens to them? They are decreasing, they are positive and they are decreasing and they are approaching 0. So this one converges to 0. You can give even more points than that. Basically, this one reminds me of the initial problem where r is between 0 and 1, the series converges. And we did this one before, and we can see the graph here. We talked about this one before. It was alternate, and we had this graph here, right? So they were convergent. So if we look at the problem, negative 1.15 to the n, I gave values to n, and I plotted the points, and we noticed that for odd numbers we have negative values, and for even numbers we have positive values, but they are increasing in magnitude, and so they are basically diverging. This one is going that way and this one is decreasing. So basically this one diverges. And we can keep in mind that if we have something like this r to the n, if r is between 1 and 0, then it converges. But if r is greater than 1, it diverges. And even more than that, we can put in absolute value. So, for example, even a negative 2 to the n is going to diverge. So this is a table of what we just talked about. If you have to calculate limit as n is approaching infinity of r to the n, if r is between negative 1 and 1, so absolute value of r is less than 1, it's going to converge to 0. If r equals 1, we're just going to get 1. And if r is strictly less than a negative 1 or strictly greater than 1, the limit doesn't exist. Here it actually doesn't exist for r less than or equal to negative 1. So at negative 1 it also doesn't converge. Squeeze theorem, if you have three sequences so that a sub n is less than or equal to b sub n is less than or equal to c sub n, if limit of a sub n equals the limit of c sub n equals L, so if these end ones have the same limit, then the limit of b sub n is going to be the same with them as well. So the most popular sequences that use the squeeze theorem are sequences that involve trigonometric functions, because just think about it, cosine of n is less than or equal to 1, greater than or equal to negative 1. So we always can figure out the other sequences. So if we divide by n squared plus 1, which is not equal to 0, then we notice that this one is approaching 0, this one is approaching 0 as n is approaching infinity, so this one must approach 0 as well. And let's quickly calculate these two limits. So limit as n is approaching infinity of n cubed over n to the fourth plus 1, well, if you calculate it's infinity over infinity, so we can do L'Hopital, but we can also say that it's equal to 0, because the denominator is the degree of the denominator is greater than degree of the numerator. While the second one, it's actually just 3 over 2, because the degree of the numerator is equal to the degree of the denominator. I hope this helps.